Welcome to the MR Physics class, lecture on basic principles of magnetic resonance imaging. We'll cover a variety of topics today. We'll begin with a discussion of gradient coils, which allow us to localize MR signals. Fourier transform, this will be a review. K-space, that's a concept of reciprocal space. That describes the environment in which we acquire our data. And then two basic MR sequences, gradient echo and spin echo MR. Here is a picture that has become very common in this lecture series. We have an excitation of a net magnetization. Remember, the net magnetization is what results from putting a sample of spins, like a head, into a large magnet, represented by this red arrow, B0 being the value of the large magnet, of the magnet's field strength. When we apply an oscillating magnetic field, oscillating at the Larmor frequency of whatever nucleus we're looking at that magnetic field strength, it causes the net magnetization to rotate away from the z-axis. And it may rotate, normally we show it in rotating in the xy plane here. It can rotate to other places also that we decide to put it. But the main idea we're going to focus on here today is what gets transferred to the xy plane where we can observe it. While we're observing it, it emits radio frequency. It's oscillating at the Larmor frequency, and we can pick that up in our detector, and that's where the signal comes from. If we're looking at a sample of just water, if you do an acquisition like this on the head, you only see a sample of almost entirely water. All the other chemicals do return a signal, but the water is thousands and thousands of times, it's hundreds of thousands of times bigger than most of the signals. So we just see this. That's clearly not an image. It's a water signal. If you show that to someone, they would say, well, it looks like there's water and probably lipid. That could describe a leg, an arm, a foot, or a head. That's a spectrum showing the frequency distribution of what we observe. Here's the acquisition, the time domain. These are the raw signals. We see this rapid off resonance oscillation that decays pretty quickly. That represents the lipid. And the overall large single exponential without oscillations, that's water, centered because we have put ourselves at the rotating frame for water. The signal is independent of location. The only location information that we have about this signal is that it's somewhere in a region that the coil can detect. So if your coil is around someone's head, you know this signal came from their head, not their foot. But we don't know anything else. The gradient, the coils provide us the spatial information that we need. So we've discussed gradient coils before, and we'll have a little review now. Here again is B0, the large magnetic field strength, and here is an example, a spin precessing around the Larmor frequency. This is an example of a spin precessing around the B0 axis of the magnet. And it's precessing with a frequency equal to gamma times B0 over 2 pi, depending on what units of gamma you use. But the main thing you got to remember is it's gamma times B0. So any variation in B0 causes the frequency to change. This gradient coil does exactly that. It changes B0 according to the location in the scanner. It's always around the Larmor frequency, but it's not right at the Larmor frequency once you move to different locations. So here we have, in the presence of a gradient, we have spins in some parts of the head, say, rotating, precessing very quickly and off of the Larmor frequency, and some precessing very slowly relative to the Larmor frequency. The gradient coils are designed to create a linear change in magnetic field strength. So if this frequency relative to the rotating frame is going twice as fast as this frequency, then and compared to this one, you can tell then what the distances are. You can tell that, well, this must have come from the middle, this came from the end, and this came from over here. So when we allow B0 to vary with space, then exactly what the Larmor frequency is can tell us where the spin is sitting. So the gradient coils are adding linear ramps to the magnetic field. So that means if B0 is now a function, say, of Z along the axis of the magnet, then as B0 rises linearly, the frequency rises linearly, and we can tell where the spins are. We've described that there are forces, very powerful forces, that are exerted when electric current goes through the gradient coils. So here is our 4 Tesla magnet. Out here is mainly where the B0 coils are located. There's an insert behind this plastic cover. That's where the gradient coils sit. So they are sitting in a magnetic field of 4 Tesla. When we run current through them, the gradient coils do their job. They create a magnetic field around them. And that magnetic field interacts with the large B0, and there's a force, just like when you try to move one magnet, you take 2 little bar magnets and move one next to the other, there's a force. That's what causes these sounds. And your research subjects are likely to ask you. Some of them will say, what causes the sound? Why is it vibrating? Shouldn't be much vibration because the gradient coils are set to move as little as possible. But people can feel it. Here is a standard MRI sequence. And now, echoplanar imaging is used for functional MRI. That requires much, much faster switching of the gradients. So these forces occur at a higher pace, a higher rate. They're happening more frequently. When there's a higher frequency of something, the pitch is higher, and the gradient strengths are often higher, so we get a louder noise. That's why we give subjects earplugs. All right, so as I described in that last slide, we have our B0 along the axis of the magnet. The gradient coils they're not just straight lines, but they are wires, or sheets of conductive material. When current passes through them, according to the right-hand rule, if you put your thumb in the direction of the current, just as was the case when we talked about radio frequency coils, you put your thumb in the direction of the current and your fingers will wrap around the wire in the direction of the magnetic field strength. Now, instead of talking about B1 when we're with a wire that's in an RF coil, we're talking G for gradient, but it's just another magnetic field. So in this case, I've drawn GX. This would be to create a change in the magnetic field along the X axis. There's also a GY and a GZ in most of the magnets. So when the gradients turn on, a DC current flows through this conductor and generates the gradient field. That's what's supposed to happen. This gradient field, however, keep in mind, it is an extramagnetic field, and there's already a magnetic field there, so there's an interaction. That causes the force that makes the noises. The gradient coils are embedded in dense, very dense, heavy material to keep them from moving and to keep them from deforming or breaking. It's possible to break the circuits because the forces are so great. You could break the joints in the conductors. You could break the form where the conductors sit, so they move more easily. And uh, eventually, gradients. That's why gradients often. Well, gradients do not often need to be replaced, but when they do need to be replaced, that is often the reason why. Next topic is a Fourier transform, which I said is a review. We won't go into the math like we did last time. In this case, what I want to talk about is where the information is distributed. As we acquire our data not as images, we acquire them in something called K-space or reciprocal space. We have to transform them to be able to see an image. This is analogous to we acquire our spectroscopy data. In the time domain, we see a time signal come out as we follow the net magnetization rotating in the XY plane, and we have to do a Fourier transform if we want to see the peaks in the spectrum. Well, we get data that look something like this picture at the upper right-hand corner, and we have to do a Fourier transform of it to convert it to an actual picture. And the reciprocal space or K-space is, for most people, that's an odd idea. It has units of 1 over distance. Now, we acquire, now the image is, this may be a strange idea also. We acquire the image in time. You open the receiver and we see these things happening while we're applying a gradient, so as I'll explain later. So you could draw a time axis on here and put seconds or milliseconds as the units. But there is something about the way we acquire them when we're acquiring them in the presence of these gradients. When the gradients are turned on, that allows us to do a conversion into this reciprocal space. There's a linear relationship between generally linear relationship between the time and the reciprocal space coordinates. That is something else that we'll talk about later. Just for now, please take it on faith that we acquire our data in reciprocal space. We do a Fourier transform and go by to real space, because remember, a Fourier transform goes between some set of units and its inverse. So we acquire our spectroscopy data in time, and we do a Fourier transform and we look at it in terms of frequency, which is 1 over time. Here we acquire our data in units of 1 over distance, and we see our pictures as distance. Here I traced a photograph of the Taj Mahal, and I did a one-dimensional Fourier transform, and this is what the reciprocal space representation looks like. Now, most people, maybe no one, could look at this and say, oh, that's a picture, that represents a picture of the Taj Mahal. So that's one of the reasons we do Fourier transforms. But I want to show you how the information is distributed. Note that the center of this is the center of reciprocal space, 0 location, is very big. And that's, if we look over here at the picture of the Taj Mahal, there are a lot of lines around it, but the Taj Mahal mainly is a big thing. There's all this space under the towers, under the main part of the building. And so that when you have a large space, there's not much changing from this part of the object to this part. Whenever there's not much changing, that means there's very low frequency sound. There's very low frequency. So we have at 0 that reciprocal space, low space frequency. That means there's not very much changing. When we go farther out, here is a rapid change. It's almost straight up and then back down. So that would call for some high frequency changes because something's happening very quickly. If we look at the lowest frequencies right around here, A, the 4 lowest frequencies, and we add them together, here's what we see. It looks like it snowed heavily on the Taj Mahal. the details are gone, but you see some object that's bigger in the middle than it is on the sides. If we go to the span B, the next 5 highest frequencies, here's what those frequencies look like. If we add them together, it's still not recognizable as the Taj Mahal, but there's a little more detail being formed. If we go to the next 20 frequencies, now we're picking up more detail. You can tell that there are actually 5 pieces to this object. And then after that, all the details are far out. They're at high frequencies. They're very far away from the center of reciprocal space. And here we are. You could see if we do a Fourier transform and we include all of the frequencies, if we take all of those frequencies and add them together with their appropriately scaled amplitudes and phases, here's what we get. You get the original object back. So the Fourier transform will go back and forth and back and forth. All the Fourier transform is saying, oh, if I have some sinusoidal waves, that I can have whatever sinusoidal waves I want, high amplitude, low amplitude, high frequency, low frequency, then what sinusoidal waves do I need to represent my object? I'm going to show a video now that that shows the K-space representation of the Taj Mahal. This in the middle is going to show what particular waveform we're looking at the moment to add to a running sum, which is going to be tracked at the bottom. Here we go. Now I'm going to pause it. We're partway out. As they see, this was blue before, now it's turning black as we move out through K-space. This is the current waveform being added, so we're at this frequency, and here is the object. If we let that run a little longer, the frequencies are I stopped it again. The frequencies are rising, and the object is beginning to pick up some more detail. And now we're to much higher frequencies, and we're really picking up. You can even see the little detail at the top of the main dome. We go to extremely high frequencies, and we're really picking up more information now. If we go all the way to the end, see how we're going farther and farther out in K-space? We're going farther and farther away from the middle, getting more and more details. Here we are. Lots of details. And eventually, you come back to the original object. There. So I will run that again. We're starting at the middle. And at the center, all you can tell really is the size of the object. If we want to know the details about the object, then we have to wait and go to look at the higher and higher frequencies. If we wanted to look at metabolites, so for NMR spectroscopy, don't worry, this is an imaging lecture, but we'll take a look at spectroscopy just for a moment here. If we have metabolite resonances in this FID, we would do a Fourier transform. We can see water, choline, creatine, and acetyl-aspartate. Now suppose instead of water, or instead of metabolites, we took vials of water. We took a couple big vials and a couple small vials, and we turned on we tipped everything into the XY plane and then turned on a gradient to change the frequencies of these. So according to this water vial is different in a different place from this water vial and this water vial. If we space these out just right and set the strength of our frequency dependence just right with the gradient, we can get something that looks exactly like a spectrum. Here, this is a peak that represents the main water peak on the left, and here's the big water peak on the right. The two little water peaks in the middle. Only now, if we do a Fourier transform, this is time or reciprocal space. Now here we're talking hertz or centimeters. There's no way to tell the difference between this and a regular chemical spectrum. Now we'll look at this information distribution a little more. If we take a Fourier transform of a square wave, which is effectively, if you took a box of water and put it in the scanner, it could look like something like this. We apply a gradient when we are observing the output from the box, the magnetization from the box. We get what's called a sinc function. And note that it's biggest in the middle, and then it has all these wiggles. The big thing in the middle represents the size of the box, mostly where nothing much is happening. So in this image, in this picture, there's nothing much happening here or here. The box itself has a long flat place up at the top. So if we're talking about spatial frequencies, there's no oscillations per centimeter of this object. It's just flat. It has zero frequency. Now at the edges, the rise and the fall, there's a lot happening. It's an instantaneous increase from nothing up to full amplitude. And that is achieved in the picture by combining a lot of spatial frequencies, some very high frequencies, because we have to come up. It's not just one frequency jumping up. There's a transition down here from nothing to something. There's a transition from this rise to another flat place, and the same on the other side. So we have a lot of wiggles at this high amplitude information. If we take the sinc function, which is what our image would, our K-space, our raw signal from an MR scanner would be, when you do a Fourier transform, you get the box back. If we do things like make the box wider, you may think about that for a moment. If we make the box wider, there's a longer flat area. So the zero area of this, the part close to zero on this sinc function, will be bigger compared to the edges. If we make this box very short, very brief, now there's a very brief, very small flat portion. So that means that the center of this, where nothing's representing nothing happening in the picture, that's going to come down in amplitude, and the outsides will increase. And you can, if you find a calculator for Fourier transform and a square wave, you can test this on your own. But that's the concept. The fewer edges we have, the more sort of middle of an object we have compared to edges, the bigger the middle of the signal is going to be. All right, now I've introduced you to the idea of K-space. Let's talk some more about how information is distributed through K-space. This is a picture of the library at Yale. I chose it because it has some details. It has some big open spaces. It has some regularly spaced objects, these bars. And if we were able to take an MRI of the library, we would see a K-space representation of it. So I'm going to do the equivalent by taking a Fourier transform of that. So if we took an MRI of the library, we would see this, except it's in color. MRIs don't have color unless we add it afterward. So we see, note that this is brightest in the middle. That's because we have a lot of very plain objects in here. There are many details, but there are windows, there are these panels on the roof, there are the panels on the walls. All of that contributes to signals very close to the middle. The signals out here, those represent all the little details in the picture. So let's say we have Kx and Ky. I'll talk most about that in MRI, but there's also a Kz. So that would correspond to the up and down or across in the magnet, up and down in the magnet, and from head to the foot in the magnet. We're going to do, if we do an MRI, we're going to have to scan this. We're going to make our measurements back and forth and back and forth. We're scanning K-space. The gradient coils are what allow us to do that. So where is the information? If we take this object and do it in a Fourier transform, like I told you, We have the low frequency components in the middle and the high frequencies out here. When you acquire an image, you want a certain field of view. Say if it's a head, you want to see all of the brain or all of a slice of the brain normally. And you want a certain number of pixels, maybe 128 or 64 or 256. You want a certain field of view and maybe a millimeter per pixel, for example. And how do you determine what field of view you get and how many millimeters you get? Well, we're sampling our data in K-space, so this is what we control to achieve the actual picture. We have the parameters n, that's the number of samples in one dimension of the K-space, and here's an n in the other dimension. They don't have to be the same. In this picture they are. The n translates directly. If you have n samples in your acquisition, you will have n samples along that axis of your image. So 128 samples here would be 128 samples here. The field of view is another thing. So you have that many pixels, but if you if you had, say, 256 pixels, and you wanted 1 millimeter per pixel, that would mean you needed a field of view of 256 millimeters. Well, the field of view is a function of how far out in K-space we go and the number of pixels. Now note, so the K max also determines our resolution. So the resolution is your field of view divided by the number of pixels. So for a 100 millimeter image and 100 samples, that's 1 millimeter per pixel. So K max is the number of pixels per field of view. So it's 1 over the resolution. The farther out, the higher the resolution you want, the farther out in K max you have to go. So here we've wiped out all of the high K values, and we're staying just near the center of K space. This is what the image looks like. So without knowing anything about K space, you could say, well, this looks like a very low resolution picture of the library. There's something going up here, but you can't really tell what it is. It may be a ramp. You see the general objects, but it's low resolution. If we want higher resolution, we have to go farther out in K space. K max has to be bigger. We go to higher sampling density of K space. That increases our field of view. So the spacing between each of the samples here is 1 over the field of view. If you sample very broadly, then delta K is bigger and the field of view will be smaller. If you want a very large field of view, you need to sample a lot of points. Let's look again at where the information is sitting. We're going to blot out the center of the transform. Just that little square here is gone. Here's the result. It looks like a haunted library. The reason it looks this way is because there's no information about what's inside the large areas. See, all of these empty panels, these panels look like they're empty. We've removed the information from them. So any large smooth areas are empty. They're gone from the image. We only have the edges and the details, and that is true for MRI as well. If we do not sample the center of K-space, we're going to see an image that is, say, of the brain is going to be the sulci, the edges of the head, the outline of the brain. In some other organ, you're going to see the edges. Now, let's take a look at deleting specific information. And I don't know why you would ever want to do this in an image, but I do this to show the relationship between spatial frequency. Actually, you can see regularly spaced objects. They have a discrete, a fairly discrete spatial frequency. And here, um, if they appear in k-space too. So let's take out the frequencies, this band that represents these railings. So some of the railings are, in reality, they're evenly spaced. In the picture, these look a little bit closer than these do, just because of perspective. But altogether, the frequencies that represent these vertical railings are located here. And you can barely see them. Now that we wipe that out, we do a Fourier transform, you can barely see them. The stairs, those are mostly unaffected because for the most part, the stairs appear horizontal, and we wiped out vertical k-space components. So the stairs, they're a little bit affected because they're not quite horizontal in the picture. There's a little bit of an angle. See here, the x-axis of the picture, and this looks like it has a slope. But it's mostly horizontal. It's vertical objects that are primarily affected. You could do this exercise for the stairs too if you wanted. So the railing spokes are gone, the stairs remain. So we're showing that the signal features contain limited frequencies. Now I told you that we acquire our data in the time domain. You open the receiver and the magnetization is precessing in the XY plane. If you put a gradient on it, then it's precessing in the XY plane at different rates from one part of the sample to another. And the computer knows, it's stored in files, what gradient strength you used, how long you acquired. So the computer is able to record where you are in k-space at any given moment and how far out in k-space you went. It knows how many samples you had. So it has all the information it needs to treat its time domain data as k-space. The reason it has is there's an equation that relates where we are in k-space relative to what the gradient is. So our location, say just for an x gradient, if we tip into the xy plane and we have an x gradient applied, where we are is equal to the gyromagnetic ratio times an integral from 0 to whenever we turn off our gradient of whatever the gradient function is. Now this gradient function can be of anything, but typically for imaging, it's flat. We turn it on and we turn it off. So typically this equation has gx at a constant for all of time that the gradient is turned on. So gx is no longer a function of time, it's just gx. So kx, outer location of kx at some time t is equal to gamma times gx times time. Gamma is the gyromagnetic ratio of usually protons, that's what we're imaging. Gx is the gradient strength in Gauss or Tesla. And time is how long the gradient has been turned on. Note that Gx and gamma, they don't change with time. They're just constants. We observe our data in the time domain, so if you want to convert our time axis for a data set to a k-space axis, you just multiply it by gamma times Gx. What happens when we actually take an image? Here is a one line of k-space. I'll explain why you have lines of k-space. Here's one line from a scan taken of a brain. What you're seeing is called an echo. So you may have heard of gradient echo imaging or spin echo imaging, echoplanar imaging. That's because this is an echo. Imagine you're standing by the Grand Canyon and you yell. First you hear your voice and then you listen. After some time, your voice comes back to you, and then the sound dies away again. Now the same thing happens with this. It's called an echo because we are refocusing magnetization that's being dispersed. Now what happens with first we turn on the gradients. This is called the read rephase lobe. I think of it more as a read prephase lobe because it comes before the read gradients. So this this gradient It does two things. In K-space terms, it's a negative, so it moves us in a negative direction. If this is the center of K-space, it moves us to negative K-space. Negative K max, actually, is where we want to go. In terms of the spins, it assigns a different frequency for each of the spins in the sample, depending on where they are, and it causes them to go out of phase. They start out all together when they tip into the XY plane, and then based on their location, rotate away from where you would see them in the rotating frame. And they get all spread out. So at the beginning, we have very little signal because the net magnetization is all spread out. It's not T2 star. It's not the star component. They're spread out in a very predictable way because we applied a gradient. And now we apply the Reed gradient. So we switch to positive, and we run the gradient for long enough to move us all the way across, back to where we came from, through the center of K-space, through Kx equals 0, and to the other edge. So this is called the Reed gradient, and it's driving us in K-space. Now, as far as the spins go, what's happening is we've applied a positive gradient, and they will gradually bring the spins back together again. So we drove them out of phase with a negative gradient, and now by applying an opposite gradient, they come back together again. At the moment where they come back together, perfectly aligned, you get an echo. You get a maximum signal, and then they spread out again according to their position. Because we know what the gradient strengths were, this is all very predictable. The computer knows what the value of Gx was for the Reed gradient, and it knows how to translate this trip across from time into K coordinates. If we do a Fourier transform, we end up with an image. Actually, the echo I'm showing you here was obtained at the Ky position of 0. So remember, we have K space in different dimensions. So when we go through the center of the Y K-space dimension, here's what the X K-space distribution looks like. We actually acquire data in the Y direction at different lines. We will record Ky equals negative K max, and a little bit more positive, more positive until we get to K0, and then so on all the way to the other side where Ky equals K max in that direction. And by getting both directions of K-space, we can get an image. If we only take that one line that I just showed you a moment ago, that's called a profile. A profile is you take a line of K-space along one direction with the other, right through the center of the other dimensions axis, and that when you do a Fourier transform of that single line, you get a profile. That is a measure of the spin density along that direction. So in this case, here's the profile for that brain slice. It's looking at how many, if you were to look at what you could see right through, how much, if you could draw a column through here and add up the image intensity, the proton density along each of these columns, that's what you would see here on the right. Here's the column at location A. Well, there's a maximum there. We're cutting through some sulci. Column B, we're going through a ventricle now, and there's a lot of signal, a lot of spin density there in the ventricle. Column C is right at the back of the head. There's a sudden drop-off in intensity, and there it is. So profiles can be of use. Sometimes you find a magnet that only has a Z gradient. It's used to get a Z profile, and what that allows you to do is to tell where your sample is along the Z axis. Basically, the question at that point becomes, did I push the sample into the magnet the right distance? Too far, not far enough, or right on? But normally, you're going to be getting images. Instead of just one line of K-space, we sample over and over. And well, first thing we'll do, say for an echoplanar image, is to drive down, turn on the negative x and the negative y gradients. Turn gradients to negative values for x and y. And that puts us down in a corner of k-space. Then we turn on a read gradient and go across. We turn on the y gradient just a little bit to move us slightly in the y direction, and we come back, and so on, and go back and forth, all the way across k-space. And I'm showing you pretty coarse sampling, because we want to sample all the dots in the picture. So this is just conceptual. Really, you have many, many crossings. Each crossing is another blip, another gradient sound, another contributor to the vibrations you feel. So most of the characteristics of the head are at the center of k-space. That's just like the Taj Mahal. See, the center is brighter than the edges. That's because the head, the first thing you would notice about a head, especially from a distance, is the size and shape. It's crosswise, it's roughly an oval. The details. Here is an image. What you would see if you were sampling k-space and watching the acquisition in real time. All right. Now something I want to point out as you go along is, see even here, this is kx and this is ky. So the amplitude here at the beginning, it's not very big, but it's still bigger than it is over the sides. So along the x direction, we're forming an echo. It's not a very big echo because we are not allowing full refocusing in the y direction. Now we'll continue the video, go a little farther. See, as we get closer and closer to the center of ky, the echo gets bigger and bigger. And there it is. And we're going right through the center of ky, and that's for the biggest echo. And as we go away in ky, the echo amplitude in kx also drops. Now, the rastered, that's called, the rastered trajectories are pretty common. They can be done slowly or they can be done very quickly, as with echoplanar imaging. But you're not constrained to that. There are diagonal trajectories. There are circular sampling patterns. There are spirals. This is a starburst. There are lots of ways to cover the k-space, to scan k-space. And which ones you use depend on a variety of things. A circular pattern is pretty gentle on the gradients. A spiral pattern is also gentle on the gradients. This rastered for echoplanar imaging demands high performance gradients if you're going to do this quickly. So a way to think about this is if you have a fast gradient set designed to be robust at high switching, then it's like driving a Ferrari. The tight corners, you can make the corners just fine. If you were trying to run a race with an old Cadillac, maybe a great big car, very comfortable, could be a powerful engine, it's not going to make those curves so well. And in that case, you want some trajectory that's going to be more gentle, and like the circular or a spiral. Each trajectory has its own demands for reconstruction, for converting the data into the time domain or k-space domain data into an image. And each one has robustness with regard to certain kinds of samples. If you were trying to image a liver that's moving around as someone breathes, or a heart that's beating, then there are some trajectories that could be more advantageous for you than others. They may be less apt to give you Martian artifacts. You can also weight different parts of k-space more heavily. Say this starburst gives you lots and lots of sampling here in the middle, and less dense sampling in the detailed regions. So one possible application for this would be if you're trying to look at bulk flow. You might take a very detailed image of the heart and then do something else where you're looking more at the center of K-space when you want to see the fluid flowing through the ventricles, which are um, large features of the heart that don't have edges in them. All right, so we'll talk about a gradient echo image sequence. This is uh, the, the sequence. This is the approach that's used most commonly for functional MRI. It's analogous to a pulse acquire experiment. It's basically a pulse acquire experiment with gradients applied so that you can be selective about where you're looking. A common thing that you'll see if you read MR methods papers is a 4-line presentation. You'll see a radio frequency or a B1 line. It just shows that we have a pulse here and it has a shape. And usually they'll show the acquisition occurring as part of the RF line. This is a transmission, and then they label the acquisition with the picture that looks like this or the label acquire. Then we have 3 gradients. They might be X, Y, and Z, but they will call them often read, phase encode, and slice. So a pulse acquire experiment is there's a radio frequency pulse, and then we open the receiver. That's a pulse acquire experiment. And note that it's subject to T2 star effects. We don't recover these inhomogeneity components like a spin echo would give you. But we usually want to see what's happening in one slice at a time. So we put on a slice selection gradient. We have a shape pulse and a slice selection gradient. And in this course, there's a lecture on shaped pulses. They're used for a variety of things, but one of the purposes of shaped pulses is that certain shapes are selective, very selective for a specific band of frequencies. So if you select, say you apply a pulse that is only going to excite 100 hertz of frequencies around the Larmor frequency, and then you apply a gradient whose gradient strength corresponds to, if you take the B gamma times the gradient strength, then you take the gradient strength translates to 100 hertz per centimeter. Then you're exciting 100 hertz, and the gradient will create a dependence of frequency of 100 hertz per centimeter. That means you excite 1 centimeter, a 1 centimeter slice through the head. That's pretty thick. Usually you'd be looking for thinner slices than that for imaging. But there's a slice selection gradient in the presence of a slice selective pulse. If we were to do this experiment, we actually wouldn't see anything. You'd see no signal. The reason is that the gradient comes on, then we do the tip into the XY plane, and at that instant there is net magnetization that's coherent. But the gradient's still on, and that's a magnetic field inhomogeneity. It will almost instantly wipe out the phase coherence in the XY plane and eliminate our signal. So we need something called a slice refocus pulse on the gradients, slice refocus lobe on the gradients. That refocuses what's lost due to the time it takes us to turn off the gradient. So this compensates for this extra bit of gradient that happens after the magnetization was tipped into the XY plane. If we do this experiment with the slice selection and the pulse, and then the refocusing lobe on the slice selection gradient, we will get a signal. You will see a water peak and a fat peak that came from one slice. You'll still not have an image, but at least you'll have a signal that's isolated to a particular slice. Well, the next thing that happens is the phase encode gradient clocks out. Now this might be, in the picture I was showing you before, this would have been in the Y direction. We do all this, and then we apply the lowest extreme on the phase encode. And then we open the receiver. We do it again, and we acquire a little not so far negative on the phase encode. and we open the receiver, and so on, over and over, and with a different step, a different amplitude on the phase encode every time. And that gives us if in the previous example, this gives us each row location for the K-space Y dimension. I've only drawn 1, 2, 3, 4, 5 levels here, but typically you would have 64 or 128 or 256. You would have, by the way, the fast Fourier transform is used, needs powers of 2, so we often choose that number of dimensions in our phase encode direction. And the other sampling direction I'll tell you in a moment. So if we do this experiment, you do this, we'll select a slice, we'll fix the magnetization, so now we have something coherent to work with, and then we go and apply this. This is driving us to negative ky. What would happen is, if we just opened the receiver, you'd see almost nothing when we were down here, and almost nothing at the top extreme, and when we had a value close to 0, you'd see you would see a signal. It would be difficult to interpret. We take all those together, we could actually create a Y profile. But there's still not an image. Now we need something called a read rephase. And I mentioned that before. I said, oh, I prefer to think of it as the read prephase. What we need a read gradient. We need to open the receiver and see what the spins are doing and measure the frequencies of the spins across the sample. But we don't want to start at the center of K-space. We want to read all the way across from the negative Kmax to the positive Kmax. And to do that, we need this negative lobe that drives us to the negative extreme of K-space. So now when we do all this, now we have an image. So we will clock out the slice selection, fix the magnetization, put it back into phase coherence. Then we'll move to the negative side of K-space and move for the redirection, and move to particular a particular phase encode location. And then finally, we turn on the read gradient and open the receiver, and we watch the magnetization move across K-space in the redirection. Now this direction often has 128 or 64 or 256 acquisitions in it. I've seen 512 before, depending what it is that you need for your image. What's your field of view desired? What is the image resolution you want? When you read a paper on functional imaging, you'll notice they say they should specify what echo delay they used. So the echo delay starts at the point that the magnetization is first tipped into the XY plane, and it ends at the center of the echo. So we go from a tip to the center, the peak of the signal. That's the echo delay. It may be 10 milliseconds, 20 milliseconds. The farther out you go, the greater the sensitivity you have to the T2 star effect. You also lose signal, so there's a trade-off. If you were to go very, very far away, you'd have a lot of sensitivity to T2 star, but there would be no signal left. Okay, so here we have K-space is going we go at a constant rate of sampling after we do this read rephase. Here's the read gradient. That's the read prephase. There's the read rephase. If we get both dimensions of XY, we can get a full image. Here's an example of gradient echo images taken from Brooker's website. They have used a variation of the sequence that nulls CSF, so that the ventricles and the sulci come out dark in these pictures, and the white matter is bright. So this is multi-slice imaging. And you can change the repetition time to get T1 weighting in the image. You can increase the echo time to increase the T2 star weighting. That's described in another lecture. And you can repeat that sequence I've shown you run it very quickly through many slices, and you get cover a large portion of the brain. Now we'll talk about a spin echo image. A spin echo image is very similar to the gradient echo image, but now we have a refocusing pulse. This compensates for most of the T2 star effects. So that's why for functional imaging, normally a gradient echo image is used. And a spin echo image will give you somewhat, you can do functional imaging with it, but it'll give you somewhat different information. So here again, we have the radio frequency line. It has now two pulses. There's an excitation pulse, and here is a 180-degree refocusing pulse. I've drawn them both with a shape to indicate that they are frequency selective. And then over here is the acquisition, also presented on the RF line. We also have the read, phase encode, and slice directions represented in the picture. All of the previous features exist in this. Here's the slice selective gradient. Here's the slice refocusing gradient. So now at this point we have coherent XY magnetization. Here are the read, rephase, the read gradients, the phase encode gradients. They all exist. What the only difference is that there's a slice selective 180-degree pulse in here. So there's the gradient for slice selection, and here's the pulse. And normally this pulse has a selectivity that in conjunction with this gradient, slice selection gradient, will select a slice of the same width as your excitation specified. So it's similar but to the gradient echo, but now there's a 180-degree refocusing pulse in the middle. The spin echo refocuses magnetization that's dispersed by the inhomogeneities, B0. And then now for this, I've said what you don't use it for. What you can use it for is normally to look at T2. You can compensate for areas with a severe T2 star loss, like the sinuses, but you can also use it to emphasize tissues that have a long T2, like CSF. So the echo delay that was specified in the gradient echo image ran from the time that the magnetization was tipped into the XY plane until the center of your echo. That's true here too, but it's a lot longer because now you've stuck a slice selective refocusing pulse right in the middle. So the echo delays for this can be longer, and even though you don't have the T2 star dropout, you can emphasize tissues with the long T2. Here is an example of a spin echo image. The CSF is bright. The white matter is dark. The reason for that is that the T2 of the white matter is shorter than the T2 of the T2 of the white matter is shorter than the T2 of the CSF. For a given echo delay, the T2 loss, not the T2 star loss, the T2 loss will be greater in the white matter than in the CSF. The gray matter is in between because its T2 is a little bit longer than the T2 of the white matter. The long TE can be used to allow short T2 tissues like white matter and gray matter to diminish their signal, and that leaves emphasis for long T2 material like CSF. Anytime you want to really light up the CSF relative to other things, a spin echo image is one approach you could use. So to summarize, the gradient coils are part of the hardware that we use to obtain spatial information about a sample. They let us excite a particular region, like a slice in the brain, and they let us observe where things are distributed through, where spins are distributed through that slice. Imaging demands a lot of spatial information and requires extensive use of the gradient coils. Remember, when you switch the gradients on and off, you have interacting magnetic fields, you get some sound, so imaging tends to be much louder than spectroscopy. Spectroscopy, the localization and the use of the gradients is generally much slower than you need for imaging, especially for functional imaging. The imaging data that we get come out in units of spatial frequency. We observe them in time, that's true, But remember that the k-space location is equal to the product of gamma times the gradient strength. The computer knows how the gradient performs. It knows how strong it is, how long you left it on. And so the computer can present your data in terms of k-space as well as in terms of time. Now, when it's in terms of k-space and you do a Fourier transform, the Fourier transform converts the k-space from spatial frequency back into regular space, so you get a picture. Gradient echo and spin echoes, those sequences are basic imaging methods. Many other sequences are derived from those, and they can be used to exploit different features of a sample to obtain the kinds of contrasts that we need for different purposes, clinical purposes, research purposes. Where is the CSF? How is the blood oxygenation changing? Has the brain decreased in volume in response to Alzheimer's disease? We can answer these questions using MR imaging. That concludes the lecture on basics of MR imaging.